into our interacting Heisenberg model that describes quantum mechanical spins on a lattice. We Fourier transformed. We got a Hamiltonian in terms of these Holstein-Primakov bosons in K-space, okay, labeled by their wave vector. And the dispersion relation that came out of that transformation was just this thing here, okay, which again you basically get by using the symmetries of this simple cubic lattice. That's where this cosine comes from. You're just going to have exponentials that are plus and minus k. And the nice thing about this is, number one, this is diagonal. It's a diagonal Hamiltonian if we work in the number basis. This dispersion for small k is the same as the classical dispersion. Right, so just proportional to k squared. That's what we found from the classical equations of motion. And what you're doing on your assignment isn't quite so simple. Which is a quantum antiferromagnet. So it's complicated by the fact that essentially after the Fourier transform in a Bogolubov, after the Holstein-Primakov transformation and the Fourier transform into K-space, your Hamiltonian's not diagonal. So a simple transcription of the classical Néel state, and the Néel state is the staggered state, right? A classical ferromagnet is, of course, all spins pointing in the same direction. Okay. There's some symmetry broken, and our magnons are deviations of those spins from all pointing in the same direction. Whereas a classical antiferromagnet, or the so-called Néel state, is up, down, is something like that. So this ferromagnetic theory is effectively classical. It's essentially classical, a straightforward transcription of that ferromagnetic state. Gives us an eigenstate of this Hamiltonian. It's diagonal as a consequence. No other steps are required. For the antiferromagnet that you're doing on the assignment, that's not true. Okay, so this isn't an eigenstate of the Hamiltonian. This is not diagonal when you do this transformation. You have to introduce this Bogolubov transformation in order to diagonalize the thing. So in the end, what you find in an antiferromagnet is you still have a symmetry breaking. You still have a staggered magnetization for the order parameter, but its magnitude is significantly reduced from its maximum classical value. So if these are spin 1/2 spins, the magnetization, so the staggered magnetization should be a half maximum, right? The expectation value of SZ operator, whereas, or the staggered SZ operator. Whereas in the spin 1/2 quantum Hamiltonian, these are spin 1/2 operators. It's actually reduced to something like 0.3 or something like that. Okay, so there's a significant reduction of the magnetization in that case. So what I'm going to talk about today is not the antiferromagnetic case, because you guys are solving that on your assignment. But I'm going to take this dispersion relationship that I calculated for the ferromagnet and calculate the thermodynamic properties or some thermodynamic properties. Question?
One thing, so when you talk about the magnetization in the antiferromagnet, I mean, if I have the staggered ground state, shouldn't the magnetization be 0?
Yeah, so the staggered magnetization.
Okay.
So the staggered magnetization is the order parameter for this classical state. So call it MS, say. So you can define an order parameter that's any, say, Fourier transform, has any wave vector. This wave vector is pi pi. So this would be like, the sum of all I, Si, Z. In 2 dimensions would be -1, Xi plus Yi. That's just actually a Fourier transform at the wave vector pi pi. Okay, so that's the order parameter for the antiferromagnet. So in a more complicated magnetic system, you might have, depending on the interactions or whatever, you could have a different wave vector for the ordering. So it could be anything. Then you would just take a general, e to the I q dot r here, and that's very common. And incidentally, neutron scattering probes that, if you want to call it structure factor, it probes that order parameter. So when you scatter neutrons off of a magnetic system, the neutrons interact with these, spin degrees of freedom, if you will, and not the lattice degrees of freedom like the phonons as much. And you'll get the full Q space dependency of all of the order parameter. So you can see peaks in that structure factor tell you exactly where, exactly the wave vector of ordering. And so these are just like the 2 simplest cases. Q equals 0, I would call that 0, 0, and this is Q equals pi pi. So let's take the Q equals 0 case, the ferromagnet, which we've calculated the dispersion for, and look at some thermal effects. So a little bit of this discussion, of course, is tied to history. So specific heats were one of the simplest things, one of the simplest bulk measurements that could be performed, in the last century. Whereas stuff like, wave vector resolved neutron scattering involves basically nuclear reactors and big spallation neutron sources and all this type of stuff. So if we can figure, if we can determine any properties of a system from bulk measurements like specific heat or magnetization, these are sort of the 0th order approach to attacking these condensed matter systems. So the effect of this dispersion relation on say something like specific heat, it follows from the same calculation that we've already done for phonons, right? All we have to do is replace the dispersion relation. So say for the ferromagnet. So the internal energy, I was writing this as U. Okay, so it's just h bar omega times the expectation value of nk. And I've ignored the sort of +1/2 that gives me the equilibrium energy contribution, because when I take the temperature derivative of that, it'll be 0. And my specific heat is just U over, so partial derivative of U with respect to T So again, sum over all k. And I can take my sum to an integral. So I have my v, and I have d3k, if you want to write it like that, 2 pi cubed. And we'll ignore any tricks that gave us the BEC in the last lecture. We'll just straight up integrate this equation like we did for phonons. Okay, so there's basically nothing you have to do different than you did for phonons, except set omega k equal to, well, whatever, some constant. I guess I'll call it d k squared. Now, this is just like the magnitude of the radial vector in k space. So again, I split this up into, I do the angular integral, I get 4 pi out of that. So 4 pi k squared dk, say. And again, I can get the temperature dependence out of this thing by basically rescaling my variables, because my temperature dependence is right here. Bring that temperature dependence out front, then I'm left with some integral. Then I could fool around with the limits of integration, set it from 0 to infinity, or be more careful, integrate over the Brouillon zone. So in this case, the change of variables, which makes the problem easy, is I just introduce a y squared. That's beta h dk squared. So I'm just going to have e to the y squared minus 1 on the bottom. And then, again, so 2y dy is all this constant 2k dk. I substitute that in for my dk here. So once I do all the substitutions, I get something out. And I'll skip all those steps. So here's my integral. I've just extended it to 0 to infinity. So that thing, you can solve it. You can get a number out of that. Once you perform that change of variables, you should have t to the 5/2, which is, this is all essentially the internal energy. And so the time derivative of that just lowers the power of t by 1. So almost exactly the same as what we did for phonons. So we get a different dependence on the specific heat out. So again, you can start to see how experimentally you might be able to differentiate contributions from phonons from those of magnons. So another nice calculation that I can do for the ferromagnet is the decrease in magnetization. Okay, so like I said, in the ferromagnetic ground state, I have a magnetization value that's whatever, it's S over the number of spins. My magnetization per spin for a spin 1/2 system would be 1/2, right? And that's not true in the Néel state for the antiferromagnet, as you'll find out. But another very simple bulk measurement for experimentalists to perform is precisely this decrease in the total magnetization as a function of temperature. Okay. So you've already done something like this in Anton's class in the mean field limit. Right, you got that mean field equation for magnetization. It's like m and then tan h and then m inside that tan h, and you solve that thing self-consistently. Okay, this is a different estimation that comes directly from the dispersion of the microscopic Hamiltonian. Remember, magnon is a deviation from SZ. All right, so if my ground state is everything pointing in the SZ direction, the Z direction, then each magnon excited decreases that magnetization. And I can calculate the magnetization. What am I going to call this thing? Maybe M. Big M. All right, so it's the sum over all SZ components. And using my transformed operators, I can just write it as NS minus A dagger A. Right, so anytime you're exciting a magnon, it decreases that total NS.
You're neglecting the term of A dagger squared, A squared, right?
The what?
The term of A squared, A dagger squared.
A squared, A dagger squared. This is like the linear spin wave approximation. Okay. Yeah, sorry. This is like linear. As with all of this, I'm just keeping it self-consistent. This is all linear spin wave theory. It's the first term of your Holstein-Primakov transformation. So it's neglecting interactions between magnons. That's what goes on in the linear spin wave theory. So let me calculate the decrease in magnetization, which is just m at t equals 0 minus this thing. So all I want is the expectation value. So my notation's inconsistent here. So this might just be the total SZ, but here I have to take the expectation value. So I don't know. There. So that's a thermal expectation value. And it's exactly like the energy calculation we just did. Where's my energy? It's exactly like the expectation value of the Hamiltonian, except it doesn't have h bar omega inside of it, right? So the only difference in my integral to calculate the decrease of magnetization is I don't have h bar omega. So the expectation value, I don't know, I'll call it delta M, which is just that sum over K skipping every step. There's no temperature derivative because I'm not looking at the specific heat. And I have a power less in the T dependence because, again, I don't have that h bar omega, which would give me higher powers. And so this thing gives me a T dependence that's just T to the 3/2. So that's a famous Bloch law, or the Bloch T3/2 law, it's sometimes called. And it's basically the classical law for the decrease in the magnetization. Okay, so if you're measuring the magnetization as a function of temperature, it's just something like that. This is a very widely applicable law. So it's used all the time. Many experiments, even experiments on exotic systems and devices that like magnetic devices that people build in modern days, if they have some sort of ferromagnetic ground state, they'll follow this Bloch law. Now, I think what you're doing on your assignment is doing this calculation for the antiferromagnet. Is that right? Yeah. So you'll see how this is modified in the case of the antiferromagnet on your assignment. But these basic steps follow through. You calculate the dispersion. The dispersion is that thing going in your integral. And from that, you can calculate the energy, the specific heat, the decrease in magnetization, and other bulk properties, which I won't touch. Questions on this?
Can you give any insight as to why the specific heat for magnons goes like 3/2 instead of 3 per planet?
The only insight is the fact that dispersion is k², and the fact that dispersion is k² came from the equations of motion, which were the equations of motion for torque, right? So basically, it has to do with somehow the angular degrees of freedom. So it's something to do with this continuous, this Lamour frequency essentially that occurs in magnetic systems. So that gives you the dispersion. This dispersion gives you the form of that law.
So phonons can be both transverse and longitudinal, but magnons can't. Is that why it's half as many?
No, I mean you still have. Okay, so you still have degrees of freedom associated with spatial directions or something, but you just have this degree of freedom associated with the magnetic, instead of just having like discrete directions, you have this sort of continuous degree of freedom associated with that Lamour precession or whatever. So maybe that's not a very good, I think the basic thing that gives a difference is always a dispersion relation. So where does that dispersion relation come from? Why is it different for ferromagnets and antiferromagnets? I mean, that's the sort of fundamental thing. If you have a system that you can parameterize the excitations not with bosons but fermions, so these sort of exotic, they call them spin-on excitations, these things can have a different dispersion and will give you different thermodynamic behavior. And people use that dispersion relation as a mechanism for detecting what excitations live in the ground state of your crystal. So you have some sort of magnetic crystal. That's your vacuum state. What are the elementary excitations? The dispersion is the thing that tells you that. And these are all consequences of that dispersion.
Question, so the graph that you have there for the magnetization somehow...
Oh, that's delta. Yeah, that's the magnetization, sorry.
So the magnetization is your order parameter, right?
Yeah.
Why in this calculation can't we see that there is critical temperature where you have a phase transition?
Well, you'll have, so that'll cross 0 at some point, and that's your phase transition in this language. But it's not a good estimate for the phase transition. Basically because we're looking at some long wavelength approximation to the omega there, and that's kind of breaking down up here in some sense. So there is, you see there's a phase transition, but this isn't the argument that you should be using to tell you what that temperature is. Okay. It's just qualitative. But it's you know, in this region, say, this is the region that you'll match with an experiment and see, you know, basically perfect correspondence. I want to move on to fermions, because you're going to have 2 weeks of fermions. And I want to get you guys ready. You poor souls. So everything we've discussed up to now has been bosonic. All the finite temperature consequences, all the second quantization notation, you know, all this stuff has been for bosonic excitations or semi-classical approximations for bosonic systems. And fermionic systems are quite different. So now I'm going to discuss the Fermi gas, the Sommerfeld theory. Get it to spell that guy's name. Sommerfeld, I think. And this is your starting point for all the discussion that's going to happen in the next 2 weeks on Fermi liquid theory and transport and exotic topological insulators and all this type of stuff. Okay, so in anticipation of, so what we're going to calculate today is some thermodynamic properties of a free Fermi gas, a bunch of free electrons. But we have to remember when we start building up the quantum theory that there's fundamental differences between fermions and bosons. And Pauli exclusion is one of those, you know, one of those properties that we can't ignore. So we've been illustrating quantization by taking a free system, like freely non-interacting bosons, and constraining them in a box, a hard wall potential. That's what gives rise to your quantization of your wave vector, right? That's why your k has discrete values. It's the same for the Fermi gas. So we can start with, say, a 3D solution. I won't write the Schrodinger equation, but so the time-independent Schrodinger equation has some solution for the wave function. That's the product of 3 solutions. Each of them gives root 2 over 3. Root 2 over L. And I'm going to label them with a quantum number n, one for each direction. So nx pi over L. So n pi over Ly. So the wave function is labeled by nx, ny, and nz, where those are integers. That's your quantization. Okay, so this is just undergraduate, you know, Griffiths. And I've been using it all along, actually. I'm just writing it explicitly. Now the energy eigenvalues associated with that solution to the 3D particle in a box problem is, you know, pi squared, n squared over L squared is your k squared. So that's k squared h bar squared over 2m. Okay, so that's your free solution. That's p squared over 2m. That's your kinetic energy. Okay, and the quantum mechanics comes in this quantization of n. So now, each energy level that's labeled by n, nx, ny, and z, can be degenerate only due to the spin value. So I'll stick with a spin 1/2 electron. So there's 2 spin values, right? So I can label my state instead of writing out the full spatial wave function. Here's my spatial part, nx, ny, and z. And then I have some sort of spin 1/2 state, ms, be plus 1/2 and minus 1/2, right? And this condition that the degeneracy is only 2, right? So comes from Pauli exclusion, right? And now what we're going to do is take this solution and basically populate a very large box. Okay, something that's has a very big volume, V. And we're going to see how this box fills up in terms of its energy levels, which are just its wave vectors k, right? Because k squared is essentially proportional to n squared. So that's a box of sides L. So let's take L to be large. So that the energy spacing is small. And this will be approximated by a continuum. This is kx, ky, kz, which is proportional to nx, ny, nz. Right, so I can imagine filling in 2 electrons, along the x direction, along the y direction, along the z direction. And because their energy is proportional to k squared, or n squared, if you will, I'm starting to fill up these energy levels near the origin first. And then I'm going to fill them out perfect, until they approximate the surface of a sphere, or the octant, or 1 octet, or whatever it's called, of a surface of a sphere. Okay? And if my L is large enough, then this approximation is pretty good. I get some sort of maybe pixelization, if you want to call it that, over the surface. But I can basically neglect that. Okay? So this is there's a certain radius. Okay, so whatever that radius is, I could call it n. Or I could call it k if I'm doing this in k space. And for large, so for large radii or whatever, or large numbers of large k or large n, that n's just like root nx squared, ny squared, and z squared. And the total number of states is just the volume of that sphere. So it's 4/3 pi r cubed. Well, r is my n. but it's only 1/8. So it's 1/8, 4/3 pi n cubed. Oh, and what did I miss? The degeneracy of 2 for the spin states. That's just times 2. 2 for the spins. Okay, so that's 1/3 pi n3. So that radius of the octant, or whatever, is also related to the energy. So the number of states gives you how much energy is inside of this sphere. And that energy is the thing that we're going to be looking at in regard to thermodynamic properties. Okay, so again, this is unique to fermions, right? I'm filling up these levels sort of 1 by 1 or 2 by 2 because of the spin degeneracy. And I'm building up this sphere in K space or in N space. And let's calculate N, the radius in terms of the energy, and the energy in, the inverse problem, and E in terms of, say, the number of states. So to do that, just take my energy equation, right? There's already an N in it there. It's N squared. So let me take the square root and then raise it to the power of 3. So from that, I get my N cubed. Which is proportional to E to the 3/2. So my NS is sort of trivially 1/3 pi times this thing. I can simplify that a bit. Okay, so if I simplify that, and what I made my L3 is my volume here, V. Then I get an expression for NS. In terms of my energy. Okay.
Why don't you have to integrate your energy? Because aren't you considering all states with up to volume N?
So this is the energy. This is the energy of that sphere when it has that radius. But yeah, you have to integrate it to get to total energy.
So shouldn't you use surface area instead of volume for the number of states?
No, so there's a number of states contained within, and that's the energy with that number of states. No, I think it's, so I mean, yes, so like the surface of this sphere is called the Fermi surface, or the Fermi energy, okay? And if I want the total energy, then I have to integrate, basically do that integral, or do that sum. So let's do that now. But so this is the number of states contained within the volume. This is the energy associated with that. And the number of states is filled up to that energy. Let's say it like that. And so the highest filled level gives you the Fermi energy. Okay, so if I'm considering if I have a number of particles in that system, so this is states. It's like shelves, right? Now I start putting books in there. So if I filled my system with a bunch of particles up to some ns, up to some radius, if you will, in k space, then the energy of those particles at the highest level is the Fermi energy. That's the energy of that level, and yeah, it still depends on the volume inside of it. So we can write this in terms of a density. I've screwed up because I've used n for the quantum numbers, and I was using n for the density before. So I can use rho, I guess. But keep in mind, so when I was writing big N over V, I guess previously I was using small n. So I'm just going to change that notation for fermions. It's because I've just been writing things in terms of k before. I just started writing them in terms of the basic quantization, the quantum number n. So the density of particles. Then I can solve for my Fermi energy. So h bar squared over 2m. That's the energy of that outer layer, that outer level, sorry. Okay? There's a wave vector associated with that. So of course, E is equal to h bar squared k squared over 2m. So the wave vector associated with the Fermi surface, or the Fermi energy, is just this 3 pi squared rho to the 1/3. That's the thing you square. And again, just because it's one special level, it's only one wave vector. It's labeled with this F. Okay, does that make sense? Just nomenclature, sort of. So now what you'll encounter lots when you do these types of calculations is the density of states. And the density of states is just exactly how it sounds. It's the number of states that occurs within some energy regime of that sphere, if you will. Okay? And the density of states allows you to write all these integrals that I've been doing over k space, and k is the same as n here, in terms of integrals over energy, okay? Which is typically how these integrals are seen. I could also have defined a density of states for phonon states or magnon states, but I just did the k integrals directly. Okay? If you start reading books and stuff, you'll see a lot of these integrals written in terms of the density of states. So I'll pick an energy range of E plus some infinitesimal dE. Okay, and so then my density of states is something I'm going to call, well, dE. Well, so if I want number of the density of states for the number of particle states in that energy regime, I take the density of states and I multiply it by the width of that energy regime. Okay, so I can calculate the density of states, or the dE in the density of states, by taking the derivative of the number ns of states, with respect to the energy. Okay, I've just taken a derivative with respect to E. Okay, so my E goes down to the power of 1/2. And I have all these constants all front, including the volume. So who's seen this expression for the density of states before? Okay, so half of you guys. So you'll basically do this quite often in either StatMech or even in a quantum class.
So this is just for 3 dimensions, right?
Yeah, so this is some 3-dimensional, because my particle in a box is 3D. Yeah.
Is there any way to write this density of states as a more general function, like for example a delta function for any dimension?
Yeah, yep, yes. It's defined via a delta function, essentially. Yeah. So I won't do that because we're just going to use this form in 3 dimensions. But yeah, there's more general expressions for this, definitely. It's essentially the delta function of, as your dE gets infinitesimally small, it's that delta function describing the number of states just right at that boundary of E that you're looking at. So you might, I don't know, depending on what happens in the next 2 weeks, you might see other forms of the density of states. But this is somehow the simple one that comes from the 3D particle in a box. Okay, so the density of states looks like e to the 1/2, whatever that looks like. And if I'm loading particles into my system, then I get occupied states up to the Fermi energy. And so the Fermi energy, again, is the energy of the last occupied level. And so it's like everything in here is occupied states. And to avoid confusion in what's coming up, this is the last occupied level at 0 temperature. This is all the 0 temperature discussion. So this density of states, so really the functional form is square root, then down to 0, right? With a sharp cutoff. So now to answer this question, the total energy of the Fermi gas is the integral. And I can integrate over K space, or I can integrate over energy space if I know the density of states. So my total energy. Now let's use my density of states. So I'm going to integrate from 0 to the Fermi energy, my energy, my density multiplied by my density of states. So that's the power of the density states, density of states in some sense. You're taking your like dk integral and you're writing it as a dE integral. Okay, so this thing just plug in all the values. And you'll find something like so that integral gives you something nice. It's actually just 3/5 times n times the Fermi energy.
I'm a little confused by what you mean like T equals 0, because if we're thinking about T as the average kinetic energy of these things, that's definitely not 0. You keep passing electrons on, they have to be constantly moving.
So as I'll get to I'm just writing this for when you look back at your notes, because when you basically go to finite temperature, you have to account for the Fermi distribution function. And that Fermi distribution function goes right here inside your integral.
So it's by T0 you need 3 minutes.
I mean the T, that's KB times T. That's the T I'm talking about there. I just said, he asked why this is T equals 0, if there's some temperature associated with the Fermi energy itself. But the T I'm talking about is, KB T. So if I have a metal at 0 temperature, what I'm constructing is a theory for that metal. And what I'm assuming, in some sense, which I haven't really talked about yet, is that the electrons in that metal act as a gas, a free Fermi gas, okay? A gas of these fermions. So at 0 temperature, the electrons in that metal, if you will, if they're free, you'll have a total energy that looks like this. And as I start to warm that metal up, I have to account for the Boltzmann, if you will, temperature, or the Fermi-Dirac distribution, which goes right here in the integral. And so that'll change this. And I'll talk about that in like 1 minute. Okay, so there's a nice relationship between the total energy and the Fermi energy. Or, I don't know if you can see that part of the board, but I'll just write it again. Which is kind of crazy. If I know the Fermi energy, then 3/5 of the Fermi energy is the average particle energy. Astounding. So anyway, so we have a sort of, third-year undergrad description of what's going on in many-body Fermi systems. And what we're interested in the condensed matter perspective is what goes on to this sort of bulk fermion system, say, as a function of temperature. So now we'll look at thermal properties. So beyond just the, non-interacting many-body quantum, oh my God, look what I did. Am I going to lose a finger here? All right, marginally better. So this simple theory that I've developed, and I've told you exactly where I'm going. I'm just going to plug the Fermi distribution function into that integral, is the theory of metals that was developed basically in the last century. And a lot of the old solid state books and a lot of your condensed matter books will just take this perspective on the field. And it's because condensed matter is an experimentally driven field, and the conductance of metals and the thermal properties of metals was basically the driving experimental force behind this field of physics, in the 20th century. So, from a condensed matter perspective, we're just going to view the electrons in a metal as being free. And I've given you enough tools that you should be highly skeptical of this assumption. So number one, I introduced you to the idea of Bloch's theorem already, which says that anytime you have a wave function in a periodic potential, there's only certain allowed values of that wave function, right? Depending on the k vector of that periodicity. And there's no mention of that periodicity in this at all. So the other thing is, I've neglected electron-electron interactions in this. So if I have many electrons, they have a Coulomb potential, right? That's E squared over A, their separation distance. And that thing is very, very strong. So somehow I'm developing a Fermi gas model of electronic systems here. And then there's no way that thing should be valid. But sort of one of the central mysteries of, I guess, the last century was the fact that this model works very well. And you're going to explore this more in the upcoming weeks. So for now, let's just assume that we have a free Fermi gas, just this quantum theory of electrons, and let's see what that says in terms of some thermal properties. So for example, what is the specific heat? So like we did before, let me think of what the classical limit of this specific heat might be. Remember we did this for phonons? I just took a limit of some integral. I don't even actually have to take I don't really have to form an integral to find the classical specific heat. Equipartition of energy just means that every degree of freedom shares equally the energy of a system. Okay, something you see in StatMech. So if you have different translational degrees of freedom, say, or you have kinetic and potential energies, the energy is shared equally between all these contributions. So in thermal equilibrium, the same average energy is associated with each degree of freedom, and that average energy is simply 1/2 kb times T per degree of freedom. And that just comes from, equipartition of energy theorem. You just 1/2 mv squared, apply, Maxwell-Boltzmann distribution. You'll get 1/2 kBT per degree of freedom. So if I say I have a particle of 3 translational degrees of freedom, so I have a gas, and then it's an electron gas, then I just sum that up, all those contributions up. I'll get a U that's kBT, right, times 3, 1/2, and if there's n particles, it's n. And that implies, if I take a derivative, then the specific heat, not 2, it's 3/2, n kb. And you've seen that before, up to some factor, because you have to be more careful how you count the degrees of freedom. But up to some factor, this is just a high temperature estimate for the specific heat that I gave you for phonons. So that's at Dulong and Petit. So in the 20th century, before the application of this quantum mechanics, that was the estimate for the specific heat of electronic systems like metals also. And the fact was that that never worked experimentally. For some reason, even at room temperature, where measurements were easily done, the value of this specific heat was like 2 orders of magnitude lower than this estimate. So we know that that's wrong, okay? And we know how to fix it. We can fix it by looking at the quantum theory. And most importantly is the Pauli exclusion principle, which gives rise to all this physics that I talked about. And the Fermi-Dirac distribution. And as you know, this is sometimes called F for some energy E. I'm going to label my E's now. So it looks very much like the Bose-Einstein distribution. So if you have a +1 there, so I get that +1 and the -1 mixed up. So that Fermi distribution function gives us, the distribution of thermalized particles. And as you know from your stat mech, so this thing just looks like a step function at 0 temperature, which is the same as saying we have a well-defined Fermi surface in that orange diagram up there. But importantly, if we thermalize the system, if we add some temperature, from the Pauli exclusion principle, we know that all the like single particle states, in the bulk of that Fermi sphere are locked into their, they're locked in, they can't move. So the essential ingredient that quantum mechanics gives us is the fact that it's the electrons at the surface, near the Fermi surface himself, that will be thermally excited and will obtain degrees of freedom associated with the finite temperature. And you see that in the distribution by the fact that at finite temperature, that thing rounds off. And it rounds off in some way proportional to, kBT. So the energy is associated with kBT. And also, the width of this rounding is much less than the actual Fermi energy. And this is just an empirical fact for most materials right up to their melting point. So a room temperature metal can be described by just a slight modification of a zero temperature Fermi distribution function. And all the actions happening basically in this region that's been excited thermally here. So when we heat up the sample, it's not all of the electrons that gain degrees of freedom, but so it's not all of them. It's only the ones near the Fermi surface. So say only those within that range, so say kBT. So the rest are locked in here. Those electrons can't move. They can't be excited, they can't lose energy, because the electronic states immediately surrounding them are all filled, and the Pauli exclusion principle won't let them. So now you have the basic ingredients that you need to take, my quantum mechanical model, plug it into just this degree of freedom counting, and give us a simple estimate for the specific heat of a metal, say at room temperature, or the thermal behavior of the specific heat. So to modify our Dulong and Petit estimate, all we want to do is swap out N for N effective. So the effective number of electrons is much less than N. Okay, so it's kBT times, so it's the energy times the density of states at that Fermi level. Okay, so that's like if we take the infinitesimal limit, so the low temperature limit, then that number of degrees of freedom is just kBT times D at the Fermi level, and all we need is so what you do is you take this Fermi energy and you plug it into your expression for the density of states. So we can do this and then just apply the equipartition of energy. And that's our simplest estimate for the specific heat. Okay, so just to finish the calculation, so sub in EF. You'll get 3/2 N over EF. Just remember how EF is described in terms of rho, the density, and this comes straightforwardly. So then NEF, the number of effective degrees of freedom, so from equipartition of energy, let's plug in this N effective into my formula up top there. So I get something like kBT squared, because I have 1 in the N effective and 1 from the equipartition of energy. 3/2 N over the Fermi energy. So this will give me a specific heat. That's proportional to T. So much different than the classical value. And all we've thrown in the calculation is like the essential parts of the quantum mechanical, statistical distribution function, if you will. So remarkably, that works really, really well. If you put in room temperature, calculate the specific heat for a typical metal, you'll get something that's 100 times less than the Dulong and Petit value. And so this is somehow one of the big successes of quantum stat mech in the early days of studying the theory of metals. But it's really, really rough. It's a really rough calculation. I've only counted degrees of freedom. And when we're dealing with bosonic systems, we did things much more carefully. We actually integrated, the U, the functional form of U, to get the total energy, and then took the derivative with respect to T. And a full calculation really needs that. So a simple way to do it, we just write it as EdE.
Roger, actually there will be the tutorial on Monday of distributing on Sommerfeld integrals.
Okay, good. I'm not doing it, so I'm just setting it up for you. You will do this on Monday. So.
Not next Monday, but Monday of Anusha's week.
Okay, so not next week, so you'll do it. All right, good. Thanks, Dennis. So I'll stop there. So you need a Sommerfeld expansion to do this. It's now the energy integral of the density of states, and I also have the Fermi distribution in here. This is. And all I'll do is give you the answer there for the specific heat, which you'll calculate, presumably. just so I can compare it to my equipartition of energy. And you see that up to some factors, as you will see, up to some factors that basically I wasn't even careful of in terms of the degree of freedom calculation, I get the same t dependence, and I get basically, you know, the same order of magnitude calculation as I got previously. So that integral is not quite as easy as the bosonic ones I did. You have to do some expansion, so some Sommerfeld expansion. Okay. So that's the basic ingredients that are going in to, you know, the free Fermi gas, or the Sommerfeld type description of metals. And important ingredients have been left out, like I said. So there was no talk of any periodicity of the underlying lattice here. And what that periodicity does, so if you apply Bloch's theorem to this, is you'll start getting band structure out. Insulators, gap, you know, conduction band, valence and conduction bands. So when you use Bloch's theorem, you'll start to recover some band structure. And from that basic band theory, I think what Shaugan's going to actually cover is, you know, a lot of the semi-classical motion transport equations that come out of this band structure. So the slightly more sophisticated theory. So I think Shaugan's going to talk about tight binding bands. He'll talk about graphene. And then he'll basically develop this theory to talk about transport. So equation of motion in energy bands. So he's deriving these Boltzmann equations for transport. So once that band theory is worked out, the other ingredient that, you know, very importantly hasn't been included is interactions. And like I said, the central mystery of why this works for metals it hasn't been addressed at all. But a combination of these topics does actually address this question. And when you start talking about interactions, Anusha will develop the language of Fermi liquid theory. And we'll see that the degrees of freedom in a metal, they're not exactly the electrons themselves. There's some electronic quasi-particle. So some quasi, you know, it's the same philosophy of you have a vacuum state, you excite a particle. In this case, you're exciting electrons near the Fermi surface. When you start to account for interactions, what you're starting to talk about is not individual electrons themselves, but quantum numbers associated with some quasi-particle, so some collective object that's made up of many electrons. But the quantum mechanics of that object is the same as the quantum mechanics of these theories. So they're well-defined particles in some sense, although they're called quasi-particles. And so the extension of the free electron gas to Fermi liquid theory, accounting for interactions, that's basically what you'll cover in the third week. It's very successful also. And once you start to develop that theory, you can look at more kind of interesting phenomena in condensed matter. So topological order, fractional quantum Hall physics, so where those quasi-particles can be fractions of the electronic charge. So there you get something that's fundamentally new in condensed matter systems, right? If you take an electron and you put that thing in an accelerator or whatever, you're never going to split that electron up. But if you take that electron and you place it in an interacting metal that has a Fermi surface, when it hits that Fermi surface, you know, depending on the vacuum state that metal has, then that electron can just naturally fractionalize at very low temperatures. So it doesn't matter how hard you hit it, you'll never split that electron up. But you can split it up inside of a material in the form of these quasi-particles. And so Shaugan and Anusha will talk a lot about that. In its extreme limit, when interactions get very strong, we have no theory. We have no working quantum mechanics. So this is the one big problems in modern physics, I would say. It's like a many electron problem in the case of strong interactions. And this is essentially why superconductivity, high temperature superconductivity is not solved. There's no microscopic, solution for the Hubbard model of strongly interacting electrons because the equations are too complex. What we've done here is we've boiled down all the equations to single particle equations. Right? The first thing I wrote on the board was like a particle in a three-dimensional box. And somehow we've taken that single particle equation and extended it to its logical limit where it applies to real materials in a laboratory. But it's a fact of life that there's materials that aren't described by these theories. So the high temperature superconductors is sort of the prime example. And so, it's too late for us old guys, but it's you kids that will develop these theories of strongly interacting electrons, I think, in the future. And I guarantee there's Nobel Prizes to be had in that. So my final gift to you is finishing 5 minutes early. So enjoy Shogun. Good luck. Enjoy Anusha. She'll be great. And I'll go downstairs to see you guys for lunch. Thank you.